Namaste and welcome to this lecture on mathematical foundations for machine learning. We are in week 10, and in the last couple of classes we have looked at the idea of matrix derivatives. We started looking at the ideas of optimization, multiple variable optimization and stuff, and we started looking at optimization problems without constraints. Now, not at all times you will have optimization without constraints. You typically you will have constraints. Within this constraints or within this boundary, you are expected to optimize the objective function, maybe to find the maximum or to minimize or maximize the objective function. You will have this. So, how do we handle these constrained optimization problems? So, that will be the focus of our lecture today. So, let us look at constrained optimization problems. It is not something that we have not seen such constrained optimization problems or anything. We are well aware of this. For example, you say that, look, I have about 20,000 rupees with me and I want to buy a mobile phone which has these features. So, I want to I want to, the constraint is that you have 20,000. The optimization that you want to do is you want to find out, you want to buy that mobile phone which has some really good features, right. So, we have already done that, or probably you go to a restaurant and then you find that, okay, this is the budget that I have for the restaurant. So, what is the best optimal food items that I can select. So, you have already done this before. It is not that we have not done, and in this case what we are going to do is we are going to look at I mean, of course, from the machine learning perspective, like where we get into constraint optimization problem and stuff. But before that we will get to do some toy problems, and then we will try to understand what is it to say in terms of the machine learning ideas. I would be doing, as I said, like the principal component analysis from as a constraint optimization problem. We will do that, right. Okay, great. So, what am I going to do now? Suppose I have an objective function. Let us assume that we have an objective function. Let f of x comma y z be the objective function. In case of our unconstrained optimization problem, we just said maximize z, say find out the value of the x and y, which would basically maximize z. I mean, that is exactly what we are going to, in fact we are going to add a small thing here. We are going to say I will put this as argmax x comma y, the function z. So, what is it that you want to find out? That value of the argument of the function, which is x comma y, which would actually maximize this function. Or you may have this other thing, argmin, you will say z, right. If you say that, this basically says that you are trying to minimize, you are going to find out the parameter which is going to minimize this function, which is basically say your x comma y. So, you either say maximize z, find the value of x comma y, or you can put this as argmax x comma y, or argmax, that means you are going to do the find out that value of x comma y which is going to maximize this z and so on. Now, what happens is, it need not necessarily be, as I said, an unconstrained problem here. So, what I would do is I would pose certain restrictions on the variables x comma y, and those restrictions would basically determine what is the maximum value of the function f, or the minimum value of the function x, and what are the parameters of what are the parameters which would help you get that maxima or minima, right. So, we are going to put some, so we impose certain restrictions or constraints. We impose certain restriction or constraints on the decision variables on the decision variables, right. We have already seen a problem like this before, where we said, look, maximize f of x comma y is equal to x y, and subject to the constraint that x plus y is equal to 100. We have seen this problem before, and we figured out the value which would do it, but we are going to look at this from a different perspective, right, where we are going to look at the use of what we call as Lagrangian multiplier. So, we are going to look at the, okay, we solve, or we introduce the idea of the Lagrange multipliers. Idea of Lagrange multipliers here, right. So, what is the use of this Lagrange multipliers, right? Okay, first of all, let us try to understand what we are trying to do here, and then we will get to the we will get to the mathematics of using this Lagrange multiplier. Say suppose I have this function f of, so the objective function is basically let us say f of x comma y, and we are going to say the constraint is going to be say g of x comma y, which will say equal to say c, some constant. Now, what am I going to do is basically say that, look, the intuitive way to understand this Lagrangian multiplier is basically the following. So, let us look at some examples here. Okay, let us make the statement. So, if, okay, let f and g be functions let us say of two variables with continuous partial derivatives, continuous partial derivatives at every point of some open set containing the smooth curve, let us say g of x comma y is equal to 0. Suppose that f, when restricted to the points on the curve g of x comma y is equal to 0, then has, let us say, a local extremum. It could be maxima or it could be a minima. We will just say it has a local extremum at, say, some point, at the point, let us say, x naught comma y naught, and that the gradient is not equal to 0. The gradient at that point, let us say, gradient of the function g this of x naught comma y naught is not equal to 0, then there exists a number lambda such that the gradient of the function f at x naught comma y naught is equal to lambda times the gradient of the function g at the point x naught comma y naught, and we call this lambda, and we call this lambda as the Lagrange multiplier. Okay, so we call this lambda as the Lagrange multiplier, and what is interesting here is, I mean, if you look at the previous expression, it actually tells us something. What is that? It says the gradient of the function evaluated at that point x naught comma y naught is a scalar multiple of the gradient of the function g evaluated at that point x naught comma y naught. Now, what do we mean by this? We know the gradient is basically a vector. The gradient of f is a vector, the gradient of g is a vector. Now, I say that one vector is a scalar multiple of another vector. What do we understand from this? We say that these two vectors are in the same direction, right? They are in the same direction, that means they are parallel to each other. You say that, okay, scalar multiple says it is lambda times, so you say that the vectors are parallel. That means the gradient vectors of the function f and the function g are parallel at the point x naught comma y naught, and that is what we are, I mean, that is exactly what we are trying to understand here, right. So, the gradient of the vector is basically the, what would you call, the gradient of the vector is basically parallel to that of the vector which is the gradient of the function g, right. So, okay, let us try to get a bit more insight, or let us try to work on it a bit more, right. Okay. Let us look at this now. Of course, we can prove this. What we will do is we will probably kind of not worry about the proof right now. We will try to solve certain problems and then understand and probably come back to the proof a bit later. Okay, fine. So, what do we do this? So, let us consider, let us take a simple example here. Example 1. So, what are we going to do and how are we going to do? Let us look at this. Let us take a simple function, let us say f of x comma y is basically x squared plus 4y squared minus 2x plus 8y, and the constraint is basically g of x comma y is equal to x plus 2y is equal to 7. And let me just put it across to you that I will be following what would you call, I will be following this the online textbook on LibreText, where you have this the chapter is titled 14.8. This is the material, I am reference material, I will put this as a reference material. This is 14.8 Lagrange multipliers. curated by Gilbert Strang. And Edwin Herman. So, this is the material that I am using. Okay, please make a note of this. This is the material that I am following for this particular topic. Okay. Okay, so let us look at this function whatever that we have taken. It says that it is going to be. So, what are we going to do? We are going to do this. So, let us try to solve. So, I am going to do this solving. So, what is the question? So, it says like find the minimum of f of x, minimum value of f of x subject to g of x. That is the constraint that we have, right. So, we already saw that the method of Lagrange multiplier involves computing the gradient of the function f and g. So, let us compute the gradient of the function f. So, the gradient of the function f is going to be what is that? This is going to be dou by dou x of the function f, and then dou by dou y of the function f. Dou by dou x of the function is nothing but with respect to x it is going to be 2x minus 2, and dou f by dou y will be 8y plus 8. This is what we have, right. 2x minus 2 and 8y plus 8. Assume that we are trying to find out at a point, let us say x naught comma y naught. So, evaluate gradient of f at the point x naught comma y naught is nothing but 2 x naught minus 2, 8 y naught plus 8. Similarly, let us find out what is the gradient of the constraint function. We have del g, which is nothing but so what is del g here? Del g is nothing but again you compute the partial derivatives. We have dou g by dou x, which is basically 1, and dou g by dou y, which is basically 2, right. Now, what are we going to do? The other term is constant. You have x plus 2y is equal to 7, that is constant. So, what are we going to do? We are going to say that look, I have my del f or at the point x naught comma y naught is going to be say some lambda times del g of x naught comma y naught. Right. So, what is del f of x naught comma y naught? Del f of x naught comma y naught is basically 2x minus 2, 2x naught minus 2, 8y naught plus 8, and that I am going to equate it to let us say 1 comma 2 lambda times 1 comma 2. So, what do we have here? If you equate this, you get 2x naught minus 2 is equal to lambda, and 8y naught plus 8 is basically equal to 2 lambda. So, now you have two expressions which are here, and so what do we have here? We have x naught 2x naught minus 2 is equal to lambda, 8y naught plus 8 is equal to 2 lambda we have, and remember we also have to compute the function. So, what we have? We want to look at g of, we have written here where the points on the curve g of x y is equal to 0. So, I am going to take g of x naught comma y naught is equal to 0, which implies what I have? I have this x naught plus 2 y naught minus 7 is equal to 0. Now, if you see, you have expressions here. We have 2x naught minus 2 is equal to lambda, then you have 4y naught plus 4 is equal to lambda. So, let us write this. So, from here this is going to be 4 y naught plus 4 is equal to lambda. I have removed that 2. So, what do we have? So, let us take this as expression 1 and let us take this as expression 2, equation 2, and let this be equation 3. So, we see that 1 is equal to 2. I mean you can put lambda, but you have 1 on the right hand side, you have lambda, on the right hand side of equation 2 also you have lambda. So, we get 2 x naught minus 2 is equal to 4 y naught plus 4, because both the right hand sides are lambda. So, what do we get? We get x naught minus 1 is equal to 2 y naught plus 2, right. We have this. From here you can substitute into the other expression, which is basically you have x naught plus 2 y naught minus 7 and so on. You can substitute and get the value of y naught. So, let us do that. So, I have x naught is equal to, from here I have x naught is equal to 2 y naught plus 3. So, what I will do is I will substitute this in equation 3, this substitute in equation 3. So, what do we have? We have 2 y naught plus 3 plus 2 y naught minus 7 is equal to 0. So, you have 4 y naught minus 4 is equal to 0, which implies y naught is equal to 1. Substitute y naught is equal to 1. So, you get 2 into 1 plus 2, which is 4, and then there is a 1 here, which implies x naught is equal to 2 y naught plus 3, which implies 5, right. We have this, and well, so you get the values of x naught and y naught. Now, let us substitute in this function. What we have is you will compute the function f of x comma y at x naught comma y naught is equal to 5 comma 1. So, if you compute, we get the values of, we get the minimum value of f of x comma y. So, which is nothing but f of 5 comma 1, which is nothing but 5 square plus 4 into 1 square minus 2 into 5 plus 8y, 8 into 1. So, we get 25 plus 8 33, 33 minus 25 plus 8 33, you get this is plus 1, 33 plus 4 37, 37 minus 10, which is basically 27, right. So, you get this. You can substitute any other point for x comma y and you will see that they are all greater than this, right. So, this is what we have. So, what have we basically done? It is another, the other way of looking at it is you can actually, the Lagrangian multiplier is used to the method of Lagrange multipliers. Allows us to convert a constrained optimization problem to an unconstrained optimization problem. To an unconstrained one. Now, how do we do this? Get the constraint as a part of your objective function itself. Let us see how to do that. Unconstrained one. So, what you do is, if the problem says minimize or maximize, let us say minimize f of x comma y subject to g of x comma y, what you do is you take this as f of x comma y. So, you basically make this as minimize f of x comma y plus lambda times g of x comma y. So, you are basically bringing in the constraint also as a part of the objective function we have, right. Okay. And basically saying g of x comma y is equal to 0. This is basically a single valued problem. So, let us take one more example and try to understand, then I will get to the idea of principal component analysis. So, let us take another example. I have example 2. Let us take this function f of x comma y, f of x comma y comma z is equal to, let us say, x squared plus y squared plus z squared, and I have the constraint is g of x comma y comma z is this x plus y plus z is equal to 1, right. Okay. So, what do? We basically get the constraint itself is now going to be g of x comma y comma z is equal to 0. So, what do we have? We have g of x comma y comma z is equal to 0 implies we have x plus y plus z minus 1, right. This is what we have. Now, of course, you can find out the gradient of this function. So, you are trying to maximize this function, let us say maximize this function. So, what are we going to do? We are going to do this business. So, I am going to get gradient of f is nothing but 2x 2y 2z, and gradient of g is nothing but 1 1 1, right. So, what do we have? We have gradient of f at x naught comma y naught comma z naught is equal to lambda times gradient of g at x naught comma y naught comma z naught, and we also have this, which is g of x comma x naught comma y naught comma z naught is equal to 0. So, what do we mean? You have if you equate this, you have 2x is equal to lambda, 2x naught is equal to lambda x naught, or 2x naught is equal to lambda, 2x naught is equal to lambda. So, this and 2y naught is equal to lambda, and 2z naught is equal to lambda, and the other constraint that we have is this, which is nothing but this condition, which is nothing but x naught plus y naught plus z naught minus 1 is equal to 0, right. We have this. Now, how do we get the values? I mean, you can see that 2x naught is equal to 2y naught is equal to 2z naught is equal to lambda. So, you can substitute and you can get the values, right. You can get the values of this one. So, let us take this. So, what do we have? We have x naught plus y naught plus z naught minus 1 is equal to 0. So, x naught is nothing but lambda by 2, y naught is nothing but lambda by 2, z naught is nothing but lambda by 2 minus is equal to 0. We have 3 lambda by 2 minus 1 is equal to 0, right. So, what do we have? We have 3 lambda minus 2 is equal to 0, lambda is equal to 2 by 3, which implies 2 x naught is equal to 2 y naught is equal to 2 z naught is equal to lambda by 3 2 by 3. Therefore, x naught is equal to y naught is equal to z naught is equal to 1 by 3. Now, you can substitute the value of this 1 by 3 in the function. So, I have f of 1 by 3 comma 1 by 3 comma 1 by 3, which is nothing but 1 by 9 plus 1 by 9 plus 1 by 9, which is nothing but 1 by 3. So, that is the maximum value that you can get, which is subject to this constraint. Now, of course, the next question that we want to ask is like, can we work with multiple constraints? Is it always that you have only one constraint that is associated with an objective function? You can always have multiple constraints. Let us take in which case you have to slog a bit more. So, let us probably look at this. Let us take a simple example here. Let us look at this. Let us take with multiple constraint, because this is precisely where we would also be looking at this in terms of our, when you do PCA, I have to look for multiple variables. So, let us just look at this. example 3. So, let me put another constraint. So, I am going to say find the minimum value, find the minimum value of x squared plus y squared plus z square subject to two x plus y plus 2z is equal to 9 and 5x plus 5y plus 7z is equal to 29. So, this is what we have. There are two constraints now. How are we going to tackle this? Simple, nothing great about it. You can actually do the understanding is like if you know it for one constraint, you can do it for two constraints. So, what am I going to do is I am going to take this. I am going to look at both constraints. So, I am going to say gradient of f at the point x naught comma y naught comma z naught is equal to lambda 1 times the gradient of the first constraint g 1, I will take it as g 1 of x naught comma y naught comma z naught plus lambda 2 times again gradient of this function g 2 of x naught comma y naught comma z naught. And the other constraints are evaluated at that point x naught comma y naught comma z naught, g 1 of x naught comma y naught comma z naught is 0, g 2 of x naught comma y naught comma z naught is equal to 0. So, if you solve this, you get the gradient of f which is already known to us. So, the gradient of f is equal to 2x 2y 2z and gradient of g 1 okay, I will just put it as gradient of f at x naught comma y naught at x naught comma y naught is going to be 2 x naught 2 y naught 2 z naught. Gradient of g 1 at x naught comma y naught comma z naught is equal to, we have the constraint to be okay. So, this is going to be 2 1 2. So, I have 2 1 2 and gradient of the second function g 2 second constraint at x naught comma y naught comma z naught is equal to 5 5 7. So, I basically have this 5 5 7 and 2 1 2. So, now I know how to do it. I am going to say gradient of f at x naught comma y naught comma z naught is equal to lambda 1 gradient of g 1 at x naught y naught z naught plus lambda 2 gradient of g 2 at x naught y naught z naught. So, what do we have here? We have 2 x naught is equal to lambda 1 into 2 plus lambda 2 into 5. Then I have y naught 2 y naught is equal to lambda 1 into 1 plus lambda 2 into 5. Then I have 2 z naught which is equal to lambda 1 into 2 plus lambda 2 into 7. And I also have this set of constraints which are basically 2 x naught plus y naught plus 2 z naught is equal to 9, and we also have 5 x naught plus 5 y naught plus 7 z naught is equal to 29, right. So, we have this. Now, you have set of equations with lambdas, and you can substitute the value of x naught, y naught and z naught in these two expressions, and you can get the value of lambdas and so on. You can solve for this, then you would end up getting the minimum function. So, I am going to have f of so the minimum is going to be minimum happens or occurs at 2 comma 1 comma 2, and the minimum value is 9, right. You can actually put all these things and then check, say 2 x naught is lambda 1 2 lambda 1 plus phi lambda 2, 2 y naught 2 z naught also you have, which is lambda 1 into 2 plus lambda 2 into 7, then y naught is nothing but lambda 1 by 2 plus phi lambda by 2, that is equal to 9. You can substitute the same thing here, and when you solve you will get this values, right. You can try this. Okay, so what is the intuitive understanding of all these things? See, whatever we have done, what is the intuitive understanding of our Lagrangian multiplier? So, the most important stuff is, if you put the constraint is going to be here. If you see, the constraint is basically a plane. If you look at the constraint that is being given to you, these two are basically planes, and even in the other case that you have is also a plane, that you have x plus y plus z is equal to 1. That means at that height it is going to cut the surface. Now therefore what we say is, it is going to act like a what do you call it, is going to be a kind of tangent to the to a level curve there. So we would be able to use this method of Lagrange multipliers to solve the problem of constraint optimization, where you convert a constraint optimization problem to an unconstrained optimization problem, right. So that is why we said that. So important thing to understand as far as gradient I mean the Lagrangian multiplier is concerned, you compute the gradient of the function, compute the gradient of the constraint. At that point where you are going to evaluate, say x naught comma y naught or whatever the point that you are going to specify, the gradients are going to be what do you call it, the two vectors are going to be parallel to each other. So one is going to be the scalar multiple of the other, and so on. So what we get is, when you solve, you will end up getting your minimum value and the argument of the and the parameters which should actually give you the minimum value. So this is what it is. Okay, great. So where do we go from here? I hope the idea of Lagrange multiplier is clear to all of you. Now what we will do is, we will stop with this lecture now, and when we come back in the next lecture, what we will do is, we will try to look at it, look at the idea of Lagrange multiplier with a specific case of principal component analysis, where we will try to find out, or we will try to establish that, look, the principal component is basically the direction of maximum variance, and that corresponds to the eigenvector of the dominant eigenvalue. We will prove that using Lagrange multiplier method, right. So yeah, so what we have done in this course is, just in this particular lecture, is we have tried to understand the constraint optimization problems. When we come back in the next class, we will look at two important stuff. One, as I promised before, we will be looking at the idea of least square solution from the calculus perspective, and the idea of Lagrangian multiplier for getting to the principal directions, principal component or principal axis. Namaste.